Welcome to Superheroes of Science. I'm Stephen.
And I'm Sarah. We co-host Science from the Experts. Our guests are professionals doing cutting-edge science right now.
They're experts in their field discussing what they know best. So listen up and learn real science from real people.
Subscribe now and stay informed of our latest episodes and show your support. Joining us today at Superheroes of Science, we are pleased to welcome Doug Schmitt, who is a Brand Professor of Unconventional Energy.
Thanks, guys.
Yes.
Yes, that sounds good.
Yeah, well, I think you're going to have to explain some of it, though, because you seem like a fairly conventional fellow to me. And so it's
right.
like, what makes you unconventional?
Okay, well, unconventional, basically, what it would traditionally mean and had in the last few years, right? There's been a lot of hydraulic fracturing, right? And so that was actually a huge amount, particularly in the U.S. and North America. And so that was one form of unconventional hydrocarbon energy, right? So the brands, right, they wanted to have more geological input into this. It's quite an engineering-driven sort of a process, right? It's like factories, right? They go and they drill horizontal holes and frack. And so, but I actually call myself the unconventional. I do some of that, or, studying the rock properties, but I also really into other aspects of energy production too, like geothermal, quite interested in, and then storage of greenhouse gases, right? CO2 underground. I've done quite a bit of that, and also what's coming is going to be storing hydrogen underground. So, all interested in I mean, that's not my entire research, but that's, kind of the broad brush of the areas where it can be applied. Right? So
Now, when you say storing underground,
right.
and so this is carbon sequestration, right?
Correct, right.
And
Yeah.
so we hear of carbon credits and things
Right.
like that, and we hear of the sequestration, but I don't think a lot of people really understands what that means.
Right.
And how that works. Could you
Right.
kind of explain that just a little bit?
I don't know that I can
Just
talk
enough?
about the legal aspects and the carbon
No, we don't want
credits.
to talk about legality stuff right now.
But
Just the
geologically and geophysically, right? So the idea and the main one, there's different forms of this, right? Would be you have porous sandstones, right? So porous sandstones or carbonate rocks, limestones. They got big pores in them, and most of them, a tiny fraction has, say, oil and gas in it, right?
Okay.
But most of them are filled with salty water, brines, right? That are way saltier than what we get in the ocean, right?
Oh.
It's sitting. Just nasty stuff, right? In fact, probably gonna be mining them for lithium, but that's another story. But the idea is to then pump carbon dioxide into the earth, into these reservoirs, right? Then over a course of years, maybe a century or maybe less, depending on the rock type and the minerals in it, that it reacts and becomes basically things like calcite, and it's locked away forever, right? So that's the idea, and pumping basically CO2 that would be stripped out of large producing sites like refineries and particularly coal-fired power plants and cement plants and steel mills. Right, and so that's basically the idea. You take the smokestack off these things, you strip out the CO2, and then you inject it into the underground so it doesn't get into the atmosphere.
Mm-hmm.
So it's really a stopgap, right? Because our energy needs are so high.
Yeah.
We're not going to be able to go to renewables overnight, right? It's going to take some time. It's happening fast, so this is going to be a stopgap for trying to get rid of some forms of CO2 from large emitters. Another interesting one that could have applications here, and particularly in Indiana and elsewhere, is actually making hydrogen, right? And then stripping the hydrogen. I mean, you make that from methane. You make that from natural gas today.
Okay.
95% or more of the hydrogen on Earth is made that way, right? Not through electrolysis of water. That's still actually very energy inefficient and expensive and difficult. And so the idea would be then to, make hydrogen still in that same manner, right? But then strip the CO2 out of the process and bury it, right? So that's stopgap. And then you can use the hydrogen for a lot of things, like steel production, right? You can get rid of coal and all of that, right? So this is one way to kind of stopgap maybe CO2 entering the atmosphere until we can make hydrogen other ways, right? That we have the technology to do that, right?
So we're going to use, I mean, there's a number of questions at this point. Trying to just figure out which one to ask.
Right.
I want to ask about the hydrogen.
Right.
Why are we making hydrogen? I kind of heard about hydrogen cars.
We make lots of. We make a lot of hydrogen already, right? A good part of you is hydrogen made from this process that goes into making fertilizer to grow food that you ate.
You say I was just full of it.
Some of it. I am too. We all are, right? So some portion of you has come from a reactor, right? Big hydrogen that went into making ammonia.
Yeah.
That is, we fertilize like crazy around the planet. We can't feed everybody without doing that. That's one big, maybe I don't know the statistics, but a pretty sizable fraction of the hydrogen on the planet goes to make that. Another big chunk goes to taking oils and adding hydrogen to them to make them better quality, right?
Oh.
And then, so you take a heavy oil, it's got a lot of carbon versus hydrogen, you got to add hydrogen to make it so it's lighter molecules.
That's
okay?
Really
Yeah. And then, so huge amounts are for that. And then huge amounts are for just about any chemical process. We're going to need hydrogen, right? So, we produce a lot of hydrogen already. But you're right? That's why. So those things are going to be there. But we could also use hydrogen for making steel and anything, or maybe aluminum and all this kind of stuff. Where traditionally we're using, coal or carbon types of chemical reactions, right?
Okay.
We just can't get away from the process of producing steel produces CO2 just because of the way you take the iron mineral and the carbon and you make steel, right? Iron. Yeah. So, but we can get away with that with hydrogen. So, and then you added in, you said transportation.
Yeah.
So there's big arguments, right, about is that going to be a viable transportation fuel? It's probably going to work in some places, right? There's fuel cells which don't really burn hydrogen, but they take hydrogen and produce water and electrons, right? They can drive your vehicles. So the problem with hydrogen as a fuel like that is that, there's transmission and all that kind of thing. It's more dangerous, say, than natural gas or gasoline or, in that sense. But its energy density isn't very high, right? So the reason we're driving, let's go back 100 years, the reason we're driving gasoline vehicles today is it's almost impossible to get a fuel that has the energy density of gasoline or diesel.
Oh.
Because lithium batteries are way down the scope on that. So you got to have like a ton or more of lithium batteries you're carrying around in your car, right? So the energy density in those fuels is why they won out in the early days, right? It just you pack a lot of energy in fossil fuels, right? But trying to get hydrogen into a form that you could have that energy density for transportation is not so easy. You might be able to do it with making ammonia, right, and burning ammonia, as one way, or maybe some other similar chemicals, right? But that's kind of the one problem we've got right now is this energy density issue, right? So,
Well, back up to the question thing.
Sure.
Just for a second here. And it's I'm envisioning if the stone is porous and it has like salt water type stuff in it, or whether it's oil they're pushing out or the water they're pushing out, and they're replacing it with CO2. But CO2 is a gas,
right?
And so, are there problems involved there with like compression?
Yes.
Is it going to compress too much? And
Right. So they compress it to high pressure and temperature. Not necessarily temperature, but the CO2 is actually a very interesting fluid because it goes into what's called a supercritical state. And actually, I don't know if you know what that is. We should be taught that in grade school, but we're not. Right? Solid, liquid, gas, right? But there's also this thing called supercritical, right? In fact, you're living in a supercritical nitrogen right now, but it's a certain phase of a gas, really.
Okay.
And so it's easy to get CO2 into the supercritical phase. You pump it to the right pressure and the right temperature. It's only about 31 degrees Celsius, right? And a pressure of about what you'd get, say, 700 meters in the earth. So, it has to be compressed to high enough pressure, right? Because you have to first get it dense enough, and then it has to be able to have the pressure to push, just the logistics of pushing fluid into another fluid with salty water in it.
Yeah.
You've got to, be able to overcome that pressure and move it, right? So it's kind of the inverse of what they do in a lot of petroleum, right? Where you're taking the pressure and lifting it up, right? So you're pushing it in. And so, so that, that's a problem. It takes energy. One problem with doing this CO2, say from a coal-fired power plant, it's pretty energy intensive itself. So just stripping the CO2 out of the flow, the smokestack, let's say, right, takes a lot of energy, right? So so that's one problem, because you got to strip it, which is energy intensive, then you got to pump it, compress it, and put it into a pipeline and have it go all the way down. Typically more than 2 kilometers, probably more than 1.5 miles, right?
Oh,
yeah.
Okay.
And so the reason is you want to be safe. You don't want it returning anywhere. You want it to be in I'll call them reservoirs, sandstone reservoirs, right? That like a petroleum reservoir, right? They'd have a cap of low permeability rock that you don't want anything to get through. It gets trapped, right, for millions of years. You hope, right? And so those are some of the problems with that. Yeah, and then there's still a lot to learn. How do these fluids move? And because it's going to be a huge amount of CO2 to do this, right? It's there's going to have to be a lot of places to do it, right? Where we are here, maybe not right here, but we don't have to go very far into Illinois, right? And there's really good reservoirs, very thick sandstones that are very old, Cambrian age, right? Filled with just salty water. There's no hydrocarbons in them, right? And so Illinois is becoming a very popular place, right? And where I was from before, Alberta, too, there's huge efforts in Saskatchewan in those sedimentary basins to store the CO2. Yeah.
And when I think of CO2, I understand the gases in the air.
Right.
But you keep saying fluid.
Right.
When you say it.
Yeah.
And then it's, from what you just said a minute ago, it sounds like it's kind of between a gas and fluid once it hits that.
It's a really neat fluid. Yeah, it is. It's actually there might be even applications for it in geothermal, and but if you wear supercritical CO2, you can replace a lot of hydrocarbons with it, right? That's say dry cleaning, right? Or when they want to make decaffeinated coffee, right? That's all actually done a lot now with supercritical CO2, right? You actually don't have to get to that high pressure and temperature to really do it. And so
I don't know how they decaffeinated coffee. I had no idea how they decaffeinated.
Well, I think there's, don't ask me, I'm not an expert, but I think there's a water process and there is CO2. So yeah, supercritical CO2, which it's almost got the density of the liquid, right? But it has, say, the viscosity of the gas, right? So it's a very interesting kind of fluid, right? And of course, it depends on pressure and temperature. Yeah. So
that was going to be my question. What are those properties of a supercritical? So it's about the density of the liquid phase, but
right. Yeah,
it still maintains the you said viscosity, so how thick.
Right. So you know, and it depends, of course, on pressure and temperature. But those are things that, if you're trying to model what's happening, going to predict what's going to happen down there, you have to take those physical properties of the fluid into account.
Interesting.
So
Well, I don't know, is this question political or not? But why would a company want to do that?
Well, right now, a lot of pressure to reduce CO2, right?
Okay.
As you mentioned, various kinds of incentives, right? There could be, depending on the jurisdiction, tax incentives, right, to get rid of it. There could be PR, right? And probably depending what you're doing, it could be the right thing to do, right? If you really want, well, okay, suppose you're making steel, and you want to use hydrogen, but to do that, you got to make hydrogen from methane. You can actually get quite a premium on your steel today. The automakers all want very little being made today. The Swedes are way ahead of us, right? And they're producing steel made from hydrogen without CO2 emissions. So if you're going to buy a car and you'll pay $5 extra, you know, okay, right? Yeah, I'll buy that car that's made. And so all the automakers want, for example, want steel made from hydrogen, right?
Okay.
So that's just one path, right? Apple wants aluminum for the cases on their iPhones and computers made from aluminum that doesn't require carbon, right? So, and hydrogen might play a role in that. You know, there's some processes out there, but they don't tell you because it's all proprietary right now. And so there's a real premium on materials, metals. I mean, that's just one.
Is there a benefit geologically to do that too? I know it's like when we frack and we pull out the oils.
Right.
Is there a benefit to then to push something in that so that we don't have settling?
Well, yeah, I don't think you could, right? One place you could, an ideal place probably to put this CO2 would be an old oil reservoir, right? And that would be a pretty, compared to the scale of it, right? You know, there's oil reservoirs here and there where you could probably do that and help with some of the settling, right? But that probably isn't going to be a major thing. Yeah.
So do they have to pump some of the salt water out of the other places to make room for the CO2 that we're pushing in?
No.
Or is it just all
you don't
compressed
want
in
to.
there?
You want to avoid bringing that up, right? That's really, you bring this super salty water up, and what do you do with it then, right? And so the idea is you push it in, and so what happens is, you know, the pressures are going to get a little higher in the reservoir and then distribute out, right? And basically you hope, or the idea is, and it should happen, right, that the CO2 will react eventually, right? And you know, that'll just fill up with brine again, right? But the fluid's going somewhere, right?
Okay, right.
And these are, you know, reservoirs. These sandstone reservoirs are, you know, typically let's say on the order of 50 meters or 150 feet thick or so. I'm just, you know, ballparking it, but hundreds of kilometers by hundreds of kilometers, right? And so if you say the pore space is 20% of that volume, think how much, you know, and you actually did the calculation on how much volume. There's a lot of volume, right? You can stuff CO2 in, right? So
would it be a lot of energy to make up for? You said this would be this would require energy to do this.
Right.
Is there a break-even point then where it?
Well,
it
I mean, that goes into the costs of all of this, right? So, you know, if there's regulatory, if you're going to be taxed, or you in one way or another, like in Canada, you're taxed, right, on CO2 emitted. Probably certain jurisdictions in the States, you're taxed, right? Other jurisdictions, you get tax credits, right? Or you may get a tax credit if you get rid of so many tons of CO2, right? So I think that's kind of one of the economic drivers of that at the present time, right? Mm-hmm. So one of the main ones, yeah.
Okay. Well, it's budgetarily wise. I mean, if you're taxing people putting extra CO2 in and, giving benefits, incentives, financial,
that's kind of right,
pay for itself.
So if you admit it, I mean, there's different models, and like I said, I don't know all these financial models all that well, but there's the taxes, and then there's credit trading and all of that kind of stuff, right? But this one is pretty solid because you measure how much you pump in and it goes away. And it's not like some of the others where you a little bit, is that really happening, right? It's harder to measure some of the other ones, right? Where you can get, when you buy an airplane, you can say give them a carbon credits. Do you really know what's actually going on? Is that how real is that, right? So this is one thing. You know how much you pump down there and it's gone, right? So it's pretty solid.
Okay, I'll give you that one. Now, some of the other forms there, because that's hopefully going to help with like coal and stuff like that, burning and offset. But then some of the other you're talking about is like geothermal.
Right.
Well, first of all, how does geothermal work, and then what's the future of geothermal going to look?
Well, I think it's going to be really good. I'll back up to this thing of energy density again.
Yes.
Saying, gasoline is pretty good and coal's okay, but everything else is, so that's one of our problems. So geothermal, if we drill deep enough, it's going to get hot wherever we are on the planet.
Another fair
statement. There is, but there's different forms of geothermal. One problem is it's even if you have hot water, its energy density isn't that high, right? Compared to so you have to move lots of fluid, or you have to move a lot of energy, usually through huge volumes of water or something like that, right? So that's one of the drawbacks. But no, I think it's a great topic, and the ones I've been involved with was drilling in Idaho, looking for geothermal energy there. But you can do this at different levels, right? You don't. You're probably thinking of generating electricity, right? And certainly we can do that, but you need usually pretty hot water to do that, right? 200 degrees C or more. Or you can use certain kinds of, they're called binary systems, where maybe you could use 100 degrees or so water, right, at the surface, right? But then there's one other aspect is basically just using it for heating and cooling, right? So if you bring up warm water, and there's in the community, right, there's a term geothermal used quite a bit, and you've seen that, and you're maybe thinking about putting a geothermal heating and cooling system in, right? I am, right, because it probably save you a lot of money, right, but it takes a few years to pay it off. But I actually don't like the term geothermal there because that's still pretty shallow, and what it's doing, but you can do systems like that that go deeper, and so the idea is if you've got any kind of, I'll call it a reservoir down there, right? You can dump heat into it, or you can take heat out, right? And so suppose you've got, say we drilled right here, and this is something I'd kind of like to push on campus, right? Could we set up some kind of geothermal system, and where we go, let's say 1 kilometer, okay? And let's say, I'm just ballparking, I don't know the temperature, but let's say the temperature is 35 degrees, 40 degrees C, right?
Okay.
And we say we bring the fluid up. We can use heat pumps with that to greatly increase the temperature of that water, right? For, say, like on campus for heating. There's the place I saw this is incredible was Lund, Sweden. So they actually take water, it's only 22 degrees C, and they pump it up into this huge heat pump, and they put it to 75 degrees C, and then they pump it into town, and it heats like a third or a half of the town, right?
Oh.
Oh, wow.
Right, and
That's impressive.
incredibly energy efficient. So the energy, there's some called a coefficient of efficiency on these things, and so the energy, it's actually these heat pumps are really good. I'm talking about lower temperature kinds of geothermal, right? Because you get about 3.5 to 5 times. So you have to use electricity. It's like a big refrigerator.
Okay.
Okay. So the back of your refrigerator is hot, right?
Right.
It's taking
Yeah.
energy out, putting it in, right?
Yeah.
And so the idea is you have this water, you take the heat out of it, you heat up something here. But that's so if you wanted to heat that, say you burn natural gas, that would be 1, okay? But the amount of energy heat produced if you advanced, right, multiplied with the heat pump, it's say 3.5 to 5 times as much. So if you can run that thing electrically, right, and instead of burning the methane, actually, yeah, you can burn the methane in a gas-fired power plant, generate electricity, and run your heat pump with say a factor of 3.5 to 5 as much heat energy you can move, and you can do that for heating or cooling. Okay, so they're this is probably going to be happening on a big scale in the future, right? They will be using these heat pumps just because they're so much more efficient than for heating and cooling than just using say hydrocarbons directly, right? So that's where I think a lot of the geothermal, say here, if we could go down a kilometer or so and find a nice sandstone reservoir or something, right? Or there's some really neat ideas now too, where instead of actually having to touch the rock, you drill a borehole like this, and you drill 2 boreholes, and they're both horizontal, and you match them up, and you seal them, and then you say run a fluid that'll collect the heat through it. So you're not, touching, you're not communicating with fluids. The fluids down there are nasty, right? So you can use something that's going to be a good heat exchange fluid, right? There's a company testing that now, actually back in Alberta, right? And so those are all kinds of new technologies that could be used to try and get that kind of lower grade geothermal energy out, right? Yeah. So, but then the fun ones are the fun ones are the hot ones, right? That's where we really need to push technology. Sorry, I got off. But because it's still hard. If you want to get down, there's actually supercritical water, and so they're testing this in Iceland. Where you have basically magma, right?
Yeah.
Close to the surface, right? Yeah. And so so they want to, if you can get to this supercritical water, not supercritical CO2, but you have to go to higher pressures and higher temperatures. Yeah. Maybe, don't quote me for sure, 350 C, and probably pressures you'd get 4 or 5 kilometers down. But then because of this issue that you have the density of the liquid, but this lower viscosity, you can move. And there's also some interesting things about this supercritical water, that it carries more heat than say just water, right? That these could be ways to really generate electricity, but you need the right geological conditions. Yeah. So.
All right. Well, let me ask you this. This might be a little out there, but
Sure.
It's what I'm known for. We have only a certain amount of oil or natural gas, petroleum on Earth. Is there only a certain amount of heat inside the Earth? If we all go to geothermal, can we actually deplete the Earth?
You're actually right. You can, right? And so, in a sense, you suppose you run a bunch of boreholes and you start pumping cold fluid through it, right? Yeah, it's gonna cool down. So you're, in a sense, say on a century time scale, you're probably mining it, right? But then it'll come back. It's slow. Conduction in the Earth is very slow. So, and the Earth is very hot down there. So it'll come back, right? But you are you are mining it in a temporary fashion.
Interesting.
That heat, right? Because and I think there is problems with that. It's the geysers in Northern California. Actually produces. It's been ongoing now for decades, right? It's geothermal energy production for. I think it produces a lot of the energy for San Francisco and the Bay Area, right?
Oh.
And that's been going on for decades. And so, I think they're running into problems where it's cooled down and, becomes less efficient, the system.
Mm-hmm.
So those are definitely considerations, yeah.
Well, help me with my foundations, basic, and this is
Right.
stuff you're like, you shouldn't be asking right now. But where's the heat come from inside the Earth?
Okay.
How did it get there?
Okay, so
Has it always been
good
there?
thing I'm teaching 118 because I remember this. Well, actually, came from different aspects, right? So one was just the forming of the Earth 4.6 billion years ago. If you slam the Earth together, there's probably more energy there in principle to vaporize it, right? So there's a huge amount of energy right from the beginning. The whole thing was probably, some people want a molten ball, right? And then it differentiated. So when it differentiated, then, you have this thing, the core, which is all quite heavy. It had to fall, right? So think about the entire core falling thousands of kilometers and how much heat energy that's going to generate. Then there was radioactive decay, right? Mm-hmm. And that's particularly in the crust, which is kind of the scum on the Earth, collects all the radioactives. So we got higher natural radioactivity here, right? And that's producing some still, right? Mm-hmm. And the fact that the inner core, this is worrisome, over a billion times. It's growing, right? It's cooling, and so as whatever iron or some kind of alloy is growing on that outer core, that's releasing heat, right? Too. So those are, there's just a lot of heat from the initial formation of the Earth, and plus that initial radioactivity and ongoing radioactivity, and that's there. So. There's a lot, yeah. I don't know how much, actually. That's a good point. I need to bring that up, put that in my lectures now, find that out. But there's a lot of heat energy down there. Yeah.
Okay.
So something I'm wondering. This might be maybe you just can help me with my foundations for this as well. But when we talk back to pumping CO2 out, or maybe CO2 that's produced back into the ground.
Right.
Is that okay? First of all, is that done right now?
Yes. Yeah.
Is it done right now?
Yes.
Okay.
Yeah. So there's been actually right next door some of the initial projects at Decatur. I'm probably saying that incorrectly because I haven't figured out my Midwest how to say names yet. Right. In Illinois. So they put about I think about a million tons of CO2 as a test project there. That actually is an ethanol plant, and ethanol has a pure CO2 stream coming out of it when we make the ethanol from corn, right? So, there's another place that you want to bury. And so that was a test, right? Okay. There's a bunch of projects being thought of right now over in Illinois and in North Dakota and in Canada and Alberta and British Columbia. Saskatchewan, there's quite a large project near a coal-fired power plant right on the border with North Dakota. So there's and then in various places, Australia, Europe, it's being tested. Yeah, for sure. Yeah.
So if there's enough, or maybe it doesn't take much, if it's pumped out of the atmosphere underground,
Well, no, we're not going to pump it out of the atmosphere.
Okay. I was like, I don't know. Okay, no.
It's the byproduct.
So it would be,
byproducts from
suppose you got a coal-fired power plant, right? And you got the smokestack coming out of it. And then you take that and you strip the...
Okay.
Yeah, so, that's one thing. It's probably not going to work on cars, and you need a large kind of source of CO2, right?
Well,
to make it.
That makes sense.
Yeah, but actually, that's one question I gave is if they. So I'm teaching the energy course, right? So one of the things I say, what are some of the problems with CO2 injection, right? That they have to multiple answer type thing. And one of them was that I said, we're going to take too much CO2 out and we'll all die or something. So you failed that one right now. I should have said that. Now they'll all get that one right.
Okay.
Assuming they all listen, yes.
I know, right?
You get your free exam question.
Yeah, that's about 1,000th of their.
Yeah, exactly. You're not going to pass the course based on that, but bonus question.
Yeah.
So what, we talk about the amount of energy that's in different fuels and stuff. What type of energy that we use as humankind is the most efficient overall?
Oh, geez. Most efficient.
Yeah, I'll put you on
I
the
guess,
spot.
well, it depends on so many things, right? So let me give you, that's maybe an impossible one to answer, but okay, I'll give 2 examples. So you may not know it, but it's more efficient in terms of energy to take the gasoline and burn it in a coal fire in a power plant, generate electricity, charge your electric car, and run the electric car, because an electric car is so much more efficient than an internal combustion engine, right? Your gasoline engine, if you get 25-30%, actually energy going down the road, you're lucky, right? So that's kind of, so it's kind of the context and the comparison, I think, that you have to do there. Another, really efficient, is the gas-fired power plant. So they do kind of a dual thing. So they take natural gas in turbines, right, and they burn it at incredible temperature, right? Because back to basic thermodynamics, if you want an efficient process, you got to have a very high temperature and a cold temperature, and the efficiency gets better with that, right? So we can never achieve that, right, in the theory, but you want to get still as high a temperature you can. And these gas-fired power plants, right? There's, I guess, one just built on campus there recently, they're incredibly efficient because they got the very high temperature. But then and I think we're looking at probably 65% or so efficiency, right? Wow. But then it gets even better, because with these things, and that's what they're doing here, they take the steam generated off that, and then they run it through a regular steam turbine. So you do a gas turbine, like, would be on a jet, essentially, right? And then, and that's very hot. The exhaust is just super hot, right? And then, so they boil water with that, and that runs steam turbines, right? So you got this 2-step process. And then you can take the warm water that's left, and I think they do that here on campus, right? And run it around for heating and cooling, right?
So, well, I had no idea.
Yeah, so you can start to get, so it's not like what's the most efficient thing, I think, is what can you do to design as efficiently as possible, right? Is probably more the way to look at it, because it's all these moving pieces sometimes, right? So, that go together and costs, of course, money and time, right, to make it more efficient. Yeah. So, but
and I didn't think about it because I've not asked an expert, but it's, you think about like the electric car,
right.
Versus, as you mentioned, versus my clunker that I drove here today.
Right. Yeah.
I'm like, is it really more efficient to drive an electric car?
Well, that's what I thought too, but you actually got some, there's some numbers out there, and it just kind of blew me away, right? Yeah. In terms of energy efficiency, right. So
I just did not think about
because those electric motors run at 85% or so efficiency, right, in your electric car. So, it's just,
Well,
I mean, that's something I learned recently too myself. So
I don't feel too bad.
I know. Well, and I think this is something, it's definitely something I've heard too, that, they're electric cars, but they have to charge from whatever. But I think that, I love that you bring up this point about the efficiency. And
but, so again, then there's the CO2 output, of course. If you're charging your electric car in Indiana, well, except we do have a lot of wind and there's going to be more solar, but, you're producing a lot of CO2, right? Yeah. If you're charging it in Norway, where everything's hydroelectric, or Quebec, right, then, no CO2, right? So, so there's that aspect of it too.
And I like to mention that I like that you talked about looking into geothermal, because I just replaced this last week my water heater.
Yeah.
I had an electric water heater. It was like literally was 55 years old. We figured out something like that.
Wow.
So it's lasted quite a while, and I was very happy with that. But we had to replace it finally. It rusted out, and I looked at, because they have the geothermal water heaters. I thought, those are a little more, but that would be really cool. But I don't have like a heat pump unit. I had to figure out what you had to have. I'm like, I can't buy one of these because I don't have a heat pump unit. I'm like, wow, if I was changing it all out or starting fresh, that'd be the way to go.
You're heating and air conditioning and your water heating, right? If you're going to start it fresh in a new house, I mean, it'd still be more expensive because you got to go and run loops in the ground and the whole thing. Or you can use. I guess we're getting way off drilling, but you can actually use dual systems that they'll have a heat pump from outside or a heat pump underground, and then it can switch to where depending what the temperature is, where it's going to be most efficient, right? Yeah.
Oh. Okay.
So I don't know how much those cost, but I mean, that's depending where the temperature is most beneficial, right? It'll grab energy either from the air or from your loop underground.
Yeah.
Right? So
Well, that's amazing. That's smart.
But again, it all costs money.
It's inexpensive.
I mean, there is so there was a talk about actually, making U.S. industry go whole, whatever that is, the presidential order to go whole hog to make peat pumps to ship to Europe to help, in the short-term period, because they're going to be going through, right, because the Russian energy problem.
Yes.
So to cut that tie entirely, or you help accelerate that, right? So so I think probably there's going to be a lot more push and rebates and stuff, I'm sure, for heat pumps coming up, right?
That's true. I think about that.
Yeah. In fact, our utilities might even, because they've got the problem here of just in the summer when everybody's running air conditioning, right? It just, keeping these grids going is not easy. Right?
That's what people don't realize, the balance they take with the number of generators they have at the different plants. And, we have to kick up another one because, it's going to be 90 degrees this week.
Right,
it's all these ACs are going to kick on. There's such a demand. And people don't, it's not just all sitting there waiting for you. It's being generated.
It's
you can't
some
generate.
poor people sweating like crazy in big control rooms, right? And making sure they can get it to you, right?
We need to have one of them on, have them explain how that works.
That would be really interesting, right?
But we need to write that down.
Okay.
We need to do that.
Talk to some at the big utilities here. They probably, I'm sure they'd do that, right?
Yeah.
Because they're worried about, I know that, they're worried about this issue, right? Because you probably got a mailer lately telling you, can we put this thing on your air conditioning that'll shut it down when we got to hit the peak hours. It saves you money too, right? Because the power prices go up. So I'm thinking of that's from the utility, right?
Okay.
To put that on our air conditioner, so that if they get in trouble, right, they'll shut your air conditioner off for a little bit just to help balance the load.
I see.
And it does pay because the prices are higher. Right? I don't know if you've been seeing what's happening in Texas. People are paying, 500 times or more the regular price for electricity, and they're ending up with $2,000-$3,000 bills, right? Because of the way the Texas system works, right? So I think it's going to force more and more people to just say, I'm going to put solar on, and sure, right? This is what it's going to do. So
Wow.
Oh wow. That's the whole topic of the future. That's everything we do. We're sitting here, we have lights around us.
I know, we're so spoiled, right?
That we are. But it's everything we do seems like it takes more and more.
Right.
Even our recreational things is, years ago, people would maybe read a book.
Right.
Where now they're reading it on a device.
And then the growth, the internet, if it continues, or just like server systems and that, if they continue on the rate they're at, they're going to be up to 20% of our energy needs by 2030 or more.
Oh my goodness.
And so everybody forgets about your little phone, but that whole backup of that whole system and that we seem to need now, right? And so, actually, I talked to he might be there was somebody in Australia thinking about energy efficient ways to run server. The great big, huge buildings, right? That they do that. All the interesting ways to try and cut energy needs, right? Because it's huge. Yeah. So.
Yeah, it's just one of those things we take for granted.
No, it is. Yeah, till it's gone.
Yes, until it's gone. Then we were like, oh wow, that was a problem.
I guess we got off drilling quite a ways, but no. Okay.
Did we not? Did we cover everything with drilling that we were going to talk about?
Well, you were going to ask what's the deepest borehole.
Oh yeah, that's what we're going to.
And then I took you off course.
Yeah.
Yeah. So okay, the deepest borehole, it's actually 12,202 meters deep, and it was drilled in the Kola Peninsula by Russia. And it finished maybe about 25 years ago, right? And there was a lot of studies, really interesting, right, there. It's closed up now. And of course, if you, in your clickbaits and that, you'll sometimes deepest hole on the earth, that kind of garbage, right?
Yeah.
Yeah. But no, it is real, right? And but unfortunately, it's closed right now. But took special kinds of developments just technically because to drill, right?
Drill that deep.
Right, yeah. Special kinds of drill strings and for the drilling process and that, plus warm, right? Then there was a deep borehole in Germany to almost 9 kilometers, right? And it got too hot. They wanted to beat the Russians, right? This was about 25 years ago, but it got too hot, right? And so heat is the thing that kind of kills you a lot. And but going, say the Gulf of Mexico, places like that now, don't quote me exactly, but it's probably a good 6-7 kilometers, right? In some of the deep basins in Wyoming and in Alberta, they'll drill to 5 kilometers, right? Fairly regularly now, yeah.
What are they doing? Why are they drilling that deep?
Well, that's all hydrocarbons, right? Yeah.
Okay.
So huge. So that was the one with the big blowout, the BP blowout a few years ago, right? They were under pretty extreme conditions, right? And plus some things went wrong, and it's extreme conditions down there, pressures and temperatures.
Yeah. Sure it is,
right? And so I always make this joke of putting something into a borehole to make measurements is actually harder than some of the space probes. They just sit out on the surface or something, right?
Well,
But you got to put something in a tube, and it has to go down, kilometers. It has to rattle the whole way, and it has to survive pressure and temperature, and sometimes pretty nasty, like these brines, right? Corrosive as can be, right? Right?
Absolutely.
So pretty nasty conditions, right?
It's tough engineering. We don't think about it. How much engineering it takes place to do the science that we're trying to figure out.
Right.
We don't even think about all of those components.
Right.
It's just mind blowing.
But there's another kind of statistic, right? The longest borehole, and don't quote me for sure, is probably on the order of 14 kilometers, and that would be off. It was, and it could be longer. I haven't checked lately, but these are horizontal boreholes that they drill from Sakhalin Island off Russia, but it was a U.S. company, Exxon, right? And they drilled horizontally that far, right?
Oh, wow.
Yeah, so it's just because of if you can drill horizontally, right, and access your reservoir, it makes much more sense than trying to just go, a pinpoint vertically through it, right? Yeah. So that's, and the technology for that is pretty interesting, right? Just how you got to steer them from so far and
that's what I'm thinking. That's crazy.
Right, yeah. So it's actually pretty impressive how that can be done, but
See, that's got to be sci-fi stuff there. I'm telling you. She gets tired of hearing me say that.
Oh no.
This is what we deal with. This is what we deal with. Everything you guys talk about, it's like, is this real or just science fiction?
Yeah.
Because it's just crazy.
Right. Yeah.
I mean, it's those are things the B movies are made from.
You're right.
Gotta get your inspiration somewhere.
That's right.
Nice.
Reality's weirder than the.
Right.
Yeah, it is.
Sometimes. Yeah. It can be. Yeah.
Well, we appreciate you taking time chatting with us.
Okay.
And
This is very interesting.
Yeah, it is.
Okay. Yeah. I guess we got off drilling, but that's okay.
Yeah, I'm saying we started on topic, and then we just kind of drifted around, then we back and forth.
Right.
We
Yeah.
did a little drifting, but I know I had more questions I was going to ask about the different how they do the drill and how they decide and all those things. But
Okay.
I started. I think I took us off track.
Well, if you get desperate later,
Oh, it'd be.
We'll have to go for a round 2 where we'll try to stay on track.
Right. Yes.
That ain't gonna happen.
we'll have a script. Right?
Right. Yeah.
The cue cards.
Yeah.
We'll have to hire somebody to stand back there and go, no, don't ask that, just ask this. That's what it would take.
Yeah.
Okay.
Well, we do appreciate your time.
Thank you for listening to this episode of Science from the Experts from Purdue University Superheroes of Science.
If you like this episode, subscribe, give us a positive review, and share the love. Boiler up!
Hammer down.